Okay, Assalamualaikum warahmatullahi wabarakatuh. Welcome to this CES 512. Uh, the topic called as Truss analysis by using stiffness metric method. So we'll start to do the learning outcomes for the topic. So at the end of the lecture, we will should be able to understand what are the principles of stiffness metrics, and we are focused on the truss. And after that, we will continue to know how to perform or to get the member stiffness matrix for a truss before it's being transformed. And after we have already obtained all of the member stiffness matrix, then we have to perform some transformations on the truss, and we perform the assembly. So the assembly will be consisting of combining all transform stiffness matrix of a truss, and this is for primarily to calculate the nodal nodes unknown by solving the solution of simultaneous equations. And once you get the nodal unknowns at the important nodes, then we'll be able to compute what are the directions and member forces. And at the end of the day, we want to solve the truss problem by using this method, what we call as stiffness metric. So not to further ado, we like to straight away to the formulations. So this is the member stiffness metric development for a single truss, which is for local. Local meaning that in the direction of the member, as established in this figure, where you can see that there are two nodal forces acting at the near nodes, which is a Qn, and another node that we call as Q far, which is far nodes. And all of the loads or the induced load will be given by this expression, EE over L times with the N, and another far ends, the forces will be the negative of it, which is EE over L dm. Okay, so we straight away to show you what are the important formula. So at the end of the day, after you perform the derivation, you will get the member stiffness metric called as K prime, which is called as EE over L with these numbers. And remember that we start the labeling the nodes here by using the near nodes and ended with the far nodes. So the same thing applies to the vertical directions here, where we apply at the top here to be the near nodes, and at the bottom we have the far nodes. So maybe I will use my pen to label here to be the near nodes, and this is my far nodes, and we have also here the near nodes and far nodes. Okay. And as you know that the members of each truss does not only lies horizontally or vertically. Sometimes they are constructed in the real construction building at a certain angles, theta x or theta y, as you can see on this diagram. Okay, so by using these direction cosines, where we can obtain the cosine in x-axis, which called as a lambda x here, and lambda y, where we compute the direction cosine for each of the angle that we are referring to. And when here there is a note here, when you label a truss member, so we will always label the near nodes and far nodes here. So you may see that here we have near nodes and far nodes here, where the arrows of the direction of the truss is given in this sense. So the starting direction of the arrow will be the near nodes, as you can see on this diagram, and the ending part of the arrow pointed features will show you the far ends. Okay, so if you want to define what are the direction cosines, which is lambda x, which is given by this formula, where is the increment or the decrement between the x direction in the far node towards to the near nodes. And the same thing also applies to lambda y, where is the increment or decrement between the y coordinates between the far node and near nodes. And if you can see carefully at the bottom here, we have an expression that is only denoting the length of that member. So even though this expression is quite complicated, but in actual it is only to calculate the member length of that truss. Okay, so by doing this displacement transformation matrix, we'll get an expression at the end of the day that we call as T. What is T? T is the transformation matrix, as you can see on the screen, where T is denoted by this matrix. So we have collection of this. And by doing so and simplifying and apply it to the force, then at the end of the day you get the force Q. So Q here is the global force on the truss, and small q here denoting your local force member, which is at the ends and in the near part. And you must multiply the transformation here after you perform the transpose. Okay, so this is the expression that will show you how to compute the member forces by using the local member forces expression by using this formula. And at the end of the day, you can compute also the member stiffness matrix, okay, which is by multiplying our transformation matrix after you have transpose, multiplied by the local stiffness matrix and multiplied by the transformation matrix. Okay, and so the final expression will be given by this lah, where you have to multiply your EE over L and multiplied by this whole term, the lambda x and lambda y, and each lambda x and lambda y is defined by this expression as given below. Okay, so in order to comprehend what we have shown here, it is better if we do some kind of examples calculation, and that will be done on the next video. Thank you.